One of the things that comes out from exponentials is scientific notation. And we want to look at scientific notation. What scientific notation is meant to do is make it easy to do some of the mathematics quickly that will be used in science. It also lets you visualize by looking at the number what the scale is of what you're measuring. To do that, scientific notation has two parts. It has what I'm just going to call A here, and then it uses an X for the multiplication sign, and it has the base 10 to some power B. Now A is greater than or equal to 1 and less than 10. So you're going to see numbers from 1 to 9.9999999 in the A portion of scientific notation. What the A does is it shows you a measure. But the unit you're using for measure comes from B. And what is happening is if I have 10 to the 0, that means I'm having A times 1, because anything to the 0 is times 1. And so A becomes the exact measure. So if I were measuring something that was 1.3 meters, in scientific notation, I'd go 1.3 times 10 to the 0 meters. And that's the same as 1.3 meters. But in science, we have a large range of things that we tend to measure. So in physics, per se, we can measure all the way down to the size of, we can measure smaller than the size of the atoms, which are 10 to the negative 10th meters. They're a very small portion of a meter, all the way up to large distances that are measured in millions of meters, especially between galaxies and such. So scientific notation lets you have this in a compact way that keeps your measurements the same. So if I were thinking of something on the size of light, that tends to be in nanometers, and so which is 10 to the negative 9th meters. And so I could say that if I'm measuring a light wave, we'll look at green light, which is the peak of sunlight, is 5 times 10 to the negative 7th meters. Well, what does this mean if we were to write it as a decimal? So what I'm going to do is I'm going to scroll this up here, give us some room. We're going to look at what scientific notation says and how we would write it into the form that we're used to. So this says that the base number is a measure of 5.50 units. But those units are 10 to the negative 7th meters. So 10 to the negative 7th is a very small fraction of meters. And we can do this by, if we write 550, and put some zeros in front of it. I'm going to put 7. And the decimal place for 550 is here. But the negative 7 tells me I need to make a small number. I need to multiply or divide by 10 7 times. We can do that by moving the decimal place over. 1, 2, 3, 4, 5, 6, 7. And so a negative 7b, or 10 to the negative 7th, moves our decimal place to the left 7 times. And so the frequency of, or the wavelength of light that comes from the sun at its peak is 5.5 times 10 to the negative 7th meters, which is 0.0. It's 1, 2, 3, 4, 5, 6 zeros there. 550 meters. And that's how we would write it. And that's how we move back and forth in scientific notation. What's nice about the notation of scientific notation here, what is nice about this, is we can see with the 5.50 that we have a measure somewhere. And the 10 to the negative 7th shows us the size. It shows us it's really small compared to the other to the meter. Now we could look at when I go hiking, I tend to measure things in kilometers or 10 to the 3rd meters. So a hike in scientific notation would be 2.0 times 10 to the 4th meters. So how would I transfer that directly into meters? I have my A here, which tells me a measure. It's saying I'm having 2 units, and the size of each of those units is 10 to the 4th meters. So I'm going to write my 2.0 here. I'm going to add my zeros to the right. Notice how we're moving in a different direction. It's because this is a positive 4 here, so my direction has changed. And so I'm moving 4 to the right. 1, 2, 3, 4. And so my answer, 1, 2, 3, 4, is 20,000 meters, or 20 kilometers. And this can happen with any form of number we use. And we'll look at a couple examples of scientific notation. So 2.147 times 10 to the 5th, we'll say that's seconds we're counting. We'll give it a unit because we're talking about measures. I would write 2.147, give myself some extra zeros here. Because it's positive, I want them on the right, because 5 is positive on the right. And I'm going to move 5, move the decimal place 5 to the right. 1, 2, 3, 4, 5. So my final number is 214,700 seconds. Of course, I'll add commas here, so it's 214,700 seconds, which that's a valid measure. Now, in the next video, we'll look at why scientists do this and why it's a nice compact notation. You should be able to see that it gives you a lot of information quickly. It tells you how big or small the thing you are measuring by looking at the B portion, or what the 10 is. So when I have something in scientific notation that's 10 to the negative 9th, this here is telling me it's really, really small. I have at least 8 things to the right of the decimal place. And when I see 10 to the 6th, I should be saying, oh, that's a big number. And scientific notation wants to say, well, this is a big or small thing right off the bat. And then the A portion, or the front portion, is the measure of how many of those big or small things we have. And the reason we keep A, I'll rewrite this here because it was up top a bit. Again, scrolling up here for you here, 10 to the B. The reason that we keep A between 1 and less than 10 is if A was 10, right, 10 times 10 to the 5th, well, our base rule says we could rewrite that as 1 times 10 to the 6th. Because I have 2 things to the same base, I can add the exponents. So to avoid confusion, we always keep A, this narrow thing, less than 10 and equal to or greater than 1. And that lets us get the most information out of scientific notation. And we'll do some multiplications with scientific notation in the next video, because it was in using this form, our exponent rules lets us do mathematics with large or small numbers rather easily.